Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, grade 12s, greetings. Alright, what we have here is a question paper from one of our fellow learners, a question paper that his teacher, sir or ma'am, not sure what the gender is, set up for them to practice before their exam, which is tomorrow. So I thought we can all stand by him as support and try and answer the question paper together with him. That way we'll surely will be lending a good helping hand. It's mostly consisting of chemistry. So we got a question 9 there, which is at the top. Some organic chemistry. Alright, question paper. And moving all the way down to question 10. Okay, so we're going to try and answer these questions as best as possible. I'll go through a few of them, etc., etc., and we'll just go through the rest. I do have all the paper, all of the question papers, although I have sent it out in, or I've asked Jaden to send it out in the group as well. So let's start with one question at a time. Let's do question 9 first. I'll let you guys engage with the question first, and then I'll jump in on the question a little bit later. Alright, so question 9. Give both names for reactions 1 to 4. So for 9.1, I'm just going to denote it like this. This is just a practice test. Okay. This is given by student teacher. Jaden, from what school? I forget.
Musenberg.
Musenberg High. Okay, cool. So 9.1. So you had 1, 2, 3, and 4. So got the question paper open there on your guys' side. Reaction 1, both names. So what type? Addition, elimination, or substitution, and the actual name for it. We'd like to answer for the first one. So look.
Substitution.
Substitution. And what type of substitution was it?
Hello. Oh.
Was it, did you say halogenation of alkanes, or?
Yeah, I think halogenation.
Okay, halogenation?
No, isn't that addition?
No, let me just cross-reference that quickly. Halogenation is an addition reaction, but substitution reaction, also you have something that's called halogenation of alkanes, okay, which is very similar to the halogenation that is found in addition. But the difference is, let me explain to you what the difference is. Halogenation as an addition reaction. Halogenation is a halogen that's added to an alkene. But remember, you have an alkane. Now, alkane is a straight chain carbon or carbonyl molecule. We say that. And with the halogenation of alkanes, that's why halogenation is just under addition reaction, but halogenation of alkanes is the full name for the substitution reaction, which means you're taking away a hydrogen from an alkane and adding in a halogen. So Matthew, you actually are correct. So it is halogenation of alkanes.
Okay.
Because it said in the question paper, if I can go back to it quickly, the first one was an alkane, which we see there. So you are 100% correct. Okay, number 2, Anybody care to share number 2? What was the reaction there? We see we got a base there as a type of catalyst, I think. KOH. What was reaction 2? What type of reaction was it? Oh, Mr. Ravens, you again. Yeah.
Elimination.
Did you say elimination?
Yes.
Okay, elimination. Sorry, I might need to change my share option here quickly so we can all see what's happening on the board.
It looks like it's changing from alkane to a alkene.
Okay, so what type of elimination reaction would that be?
Dehydration. No, dehalogenation.
Dehalogenation. So elimination. So we got dehydrohalogenation, dehydration. So it'd probably be dehydrohalogenation.
Dehydro. But
Yep.
we have 2 bromines.
Let me see. So the only type of elimination reactions we get is, so for the substitution of alkanes, only one bromine will join with in substitution of that one hydrogen, I think. And then a byproduct will form as like HBr, hydrogen bromide. A byproduct will form.
Okay.
So I think it is dehydrohalogenation.
Yeah.
Just check so far. Does anybody agree or disagree? Any disagreements? Judging by the silence. There is agreement. There is agreement. There is agreement. I like the agreement. I like the agreement. I like it a lot. All right. Reaction 3. Let's go check what that was. Okay. Which is this arrow here. Number 3. You've got CH2, CH, CH3. 1, 2, 3. Okay, cool. And then we go through to an alcohol. So reaction 3B. Anybody? So we're going from an alkene, CH2, CH, CH3. We're going from an alkene to a alcohol. What type of reaction is that? Addition, hydration. Thank you, Zuleika, in the chat. Is addition, and it is hydration. And then the last one, we go from alcohol, and this is where it's not very clear. I'm not sure what it goes to.
So
Jaden, yeah, sorry. Yeah, Jaden, shouldn't that be an ester at the end there? This is your question paper, so I think
it should.
Yeah, I think based on that. Sorry. Matthew's got good eyes there. Let me just erase my error here. That's what I need. Alcohol, and then it goes to an ester. So that is just esterification. And I only know it to be one word, by the way, because you got an alcohol there, and sorry, let me just zoom in a more. And there, that's a carboxylic acid there on top there. So alcohol with that gives you will give you an ester at the end there. So that's reaction 4. Sorry about that, ladies and gentlemen. Okay, 9.2, name B and E. Okay, so Not sure. B is a little bit simple, I think, because alkane and then it becomes something, so we can name B. But E, I think, is the name of the ester. Okay. Just to eliminate any confusion. So 9.2. Change the color up slightly. Okay. What is B and what is E? Can someone name B for me?
Is it perhaps 2-bromopentane?
I'm trying to see. Would it be pentane? If I count 1, 2, I count 3 carbons here.
Pentane is 3, isn't it? Or
Oh, you getting confused with 5 and 3. You
mean
bromo propane.
there we go.
propane?
There we go. Propane. So that would be 2-bromo. Propane. Excellent. That was quite a basic one. Okay, 2-bromo-propane. And E, I think, is the combination now of the ester. So you obviously know, I think the alcohol would be propanol plus the carboxylic acid there, which looks like to be ethanoic acid, because there's only 2 carbons there. So ethanoic acid plus propanol, the name of the ester should be. It is actually quite difficult to interpret if the E is the alkane, which is just given as alkane, or if they actually want what is the name of the ester itself. I'm going to interpret it as the type of alkane that it is. So because it's right underneath it there in its place, and this would be, I think E goes for this one here, I'm sure. Yeah, so I'm gonna say E should be the name of the alkane, which should be just propane. Actually, sorry about that, guys. I don't know why that right click happened there. Yeah. Okay. All good then. Okay, E, I'm gonna say rather is the name of the alkane. That's just how I am interpreting the question. 9.3, name the catalyst and condition needed for reaction 4. So that's esterification. Okay, name the yes, that's right. Name the catalyst and also the reaction condition for reaction 4, which would be obviously which we decided or which we interpreted as esterification. Okay, there is a condition for it. And also a catalyst. Does anybody know? Anybody know? Reaction condition and the catalyst needed. Well, for a ester can only be prepared, 9.3, in the presence of a strong acid. So in the presence of a strong acid would definitely help in the formation of a ester, of course, which is basically all I have in my notes as well. Okay, when it comes to esterification, just check it, make sure I'm not missing anything from that. No, I don't think I am. Nope, that's it. Okay, just in the presence of a strong acid. That's all all my notes say about esterification, or in the presence of esters, is that it can be prepared between an alcohol and a carboxylic acid in the presence of a strong acid. which is, so you can take either methanol and ethanoic acid, and your catalyst would be carboxylic acid, your sulfuric acid, for example, and that would be a good catalyst for that. Okay, that's all fortunately we can say, so we can name the catalyst there as H2SO4. Okay. 9.4. List the conditions needed for reaction 3, which is hydration. Okay, do we remember this? The reaction conditions needed for hydration. Anybody know one? Okay, one of those must be the alkene. Must be dissolved in a non-polar solvent. In H2 atmosphere, so in the presence of hydrogen, H2 atmosphere, and there must be the presence of a catalyst. Catalyst, i.e., must be nickel or platinum or lead. Catalyst, PD. That's the two reaction conditions for hydration, which is reaction 3. Question 11. At the top there, they've given us the amount of the molar masses of the substances there. And question 11.1, they say if N is equal to M over big M, which is the number of amount of moles, or number of moles is equal to mass divided by molar mass, and the concentration is equal to the amount of moles divided by the volume, and we have 11 grams of NaOH, which is sodium hydroxide, in 4 decimeters cubed of water, then what is the concentration of the solution in moles per decimeter cube? So they're asking you calculate the concentration of sodium hydroxide. They've given you the mass of sodium hydroxide, and they've also given you the volume, okay? And they've given you the two formulas. So what I would do, if I were you, is combine them and get an answer. Alright, so they gave us, of course, the formula that we all know so well, M over big M, and of course C is equal to N over V. Alright, so in this case, the substance they gave us was NaOH. The volume was equal to 4 decimeters cubed. Alright, so with this one, obviously we can see N is equal to mass divided by molar mass, and we have N here in this formula, so we form a hybrid formula. C is equal to M over MV. Okay, once we have that, so we got 11 grams of that substance. The mass was equal to 11 grams, and they asked us to calculate what the concentration was. So we've got 11 divided by the molar mass. So let's go have a look at what those numerical values were. The molar mass of NaOH is equal to Na is 23, so 23 plus 16 plus 1 should be 40. Okay, 40 grams per mole. So we've got 11 divided by 40 times by 4. Okay, so we have 11 over 40 times by 4. Amount of moles that we should, or the concentration rather, I don't know why I said amount of moles. Concentration should equal to 0, to 2 decimal places, so that's 0,06875. So I'm going to round it up to 0,07 mole per decimeter cubed. Alright, so we can see we got a bunch of follow-on questions for 11.2, 11.3, 11.4, and 11.6. And then obviously question 12 as well, but we just focus on question 11 now. So question 11.2 all the way through to 11.6 is still making use of the same formulae, just asking us to calculate different things, and they're all 2 marks each. So 2, 4, 6, 8, 10. So another 10 marks worth of questions. We just completed the first 2, so 12 altogether. I'm going to give about 10 minutes for question 11.2 all the way through to 11.6, and then we'll mark it. Right, so the nature of these questions for question 11, grade 12s, 11.2, 11.3 is the same type of question. They just made a few numerical changes as well as some substance changes, so molecule changes, compound changes. I'm going to start off marking 11.4. 11.4's question is the same introduction, but now we have 2 decimeters cube solution of potassium permanganate with a concentration of 2 moles per decimeter cube. So in this question, that's different from the previous 3, is that we are given the volume and now the concentration, and now we are asked to calculate the mass. Okay, so let's have a look at 11.4. We are given the volume, which is 2 decimeters cubed. We are given the concentration, which is 2 mole per decimeter cubed. And we are also given the substance, which is potassium permanganate, KMnO4. And let's find the molar mass of the substance while we're at it. So over here, sorry, let's just zoom in slightly. So potassium permanganate, so potassium, we got 39 plus 55 KMnO4 plus 4 times 16, that's 158. Okay, so that's 158 grams per mole. Okay, so now let's type in this question. So we can combine the formulae again. C is equal to M, big M times V. So we are given 2. Let's just double check that it is 2. 11.4, yes. We are given 2 is equal to the mass, all divided by the molar mass, which is 158, times by 2. What we could have done is worked it out separately. We could have worked out the number of moles first, and then substituted that into the mole formula, or we could just combine it and use both. 158 times 2 equals 316 at the bottom here. So we multiply both sides. Yes, that's correct. That cancels. That cancels as well. Multiply that by 2. I think everything's in the right units. And 316 times 2. So the mass should equal 632 grams. Now, how we can obviously check that, if maybe we got different answers, can check that by actually doing it the longer route. So we're given C is equal to N over V. So let's see, 2 is equal to N, and the amount of the volume was also 2. Yes, 2 decimeters cubed, and volume was 2. Okay, cool. Let's come back here. So the amount of moles is going to equal to 4. Sorry, I wrote it back to front. So now we can substitute that into N is equal to M over big M. So 4 is equal to mass divided by 158. So 158 times by 4 gives us still the same answer, 632 grams. Same answer. Okay, so don't let it fool you. It's a big number. Okay. 11.5. 11.6 is the same nature, it's just different numbers and different substance. 11.5 now says they now give us 4 decimeters cube of sodium hydroxide with a concentration now of 1 mole per decimeter cubed, what is the mass of sodium hydroxide? So again, C is equal to the combined formula M divided by big M times V. Concentration was 1. The mass of NaOH is still unknown. All over, I think it was 40 times 4. Okay? Which is 160. So 40 times 4 here cancels, which ends up being 160 here times 1. Therefore, the mass of NaOH is equal to 160 grams. Okay? 11.5, 11.6, like I said, is the same nature, different numbers, different substance, the same nature of the question. All good. So I'm not going to do 11.6, it's going to be a bit tedious. Okay. Hope that makes sense for everybody. So let me just take some time to explain the Chateliers principle, which was one of the questions in the paper which was provided. The Chateliers principle defined is when equilibrium in a closed system is disturbed. So in other words, equilibrium has already been reached and now it's disturbed. When it has been disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. Okay, so a imposed disturbance could be what happens if there is a temperature increase. All right, if there is a temperature increase for a certain reaction, a temperature increase, we would expect equilibrium to maybe shift to the right, but the reaction will actually oppose that. So instead of shifting to the right, it will aim to shift to the left rather. So if there's a temperature increase, okay, then that means the equilibrium will shift to the left, meaning that instead of favoring the forward reaction, which would be an obvious shift to the right, it now opposes that change and favors the reverse reaction. Let's have a look at a reaction quickly, and let's draw some graphs to have a look at it. Okay, so the reaction, let's take SO2 gas plus O2 gas. It's a reversible reaction. And of course we get SO3 gas. Okay, with enthalpy being less than 0, we should remember from grade 11. And we balance the equation. So that should be O2, we have O3, so 2 and 2. Okay, so first of all, the imposed disturbance is what happens if I increase the temperature. What does that result in? Increase temperature, which would be the forward reaction would be an exothermic reaction. Anything that reacts with oxygen, exothermic. But the reverse would be endothermic. So the imposed disturbance, which is increasing temperature, okay. Now, with equilibrium, of course, we take into consideration concentration. So how the concentration of the reactants is going to look will look something like this. Let me see. What's the best way to describe this now? Quickly, give me a minute. Let me first say this. So increase in temperature would basically cause equilibrium to shift left. EQ to shift to the left. Okay? Meaning the reverse reaction is favored. Okay. This only exists under Le Chatelier's principle. Okay? So the reverse reaction is endothermic of this reaction. So, if I draw a graph of the concentration, okay, so this is either the number of moles either number of moles, or this is concentration on the y-axis, and then on the x-axis we obviously got time, but it's in minutes, not seconds. Okay, so I'm going to use some color here. So let's say for oxygen products, okay, reacts, okay, then it phases out there, and then it does some type of lift, then it phases out there. This is of oxygen, the concentration of oxygen over time. Let's use another color for SO2. Then it does the same thing. Okay, the concentration of SO2. Alright. And then the products form. Slightly different now. And there we go. This is the concentration of SO3. So now we've got an increase in temperature here, and what happens to the concentration? Okay, so these actually were supposed to form in one line, so let me just get them all to form one line here quickly. There we go. There we go, that's better. So around about here, roughly one line. Okay, and roughly here as well is one line. Okay, so let me just fix this a little bit. Fix this up a little bit here. Okay, there we go. There we go. Okay, cool. So, sorry it took so long there. So I've got obviously T1, T2, and over here basically where they flatten out, like all around here. Sorry, very bad line. Around about here, we've got T3. Okay. So we can see obviously the number of moles or concentration of over time. We can see that the reactants obviously concentration therefore increase, the products went down. Okay, now this is the graph of concentration of reactants and products as a result of a temperature increase. Usually with a temperature increase, alright, that is not under Le Chatelier's principle, or a reaction that has not reached equilibrium, would obviously result in more products being made, okay, under the topic of energy and chemical change. But now under Le Chatelier's principle, obviously now we are dealing with equilibrium in a reaction. So now that equilibrium is now reached, and now we have disturbed that equilibrium. So now the equilibrium is now aiming to reverse or oppose that change. So now that we have seen what happens with the temperature increase, which is the only example I have time for tonight to use, I got time in minutes, right? And this time I'm now graphing the reaction rate. Now the reaction rate we know, which is products change in products or change in reactants over change in time. Okay, I'm just going to use minutes because I can't write the full word in there for minutes. Okay, so the forward reaction, all right, would obviously be like this. It would go down, okay, mellow out like that, okay, and then it would somehow increase like that, okay, for the forward reaction. Okay, but remember the reverse reaction is favored, so that reverse reaction I'm going to have to use another color for. Okay, so it's also going to come to the same point around about here, also mellow out like that. Okay, just change that line to make it more straighter. There we go. And then all of a sudden it's going to shoot up. like that, and then mellow out again. Okay, like that. Okay, so the white is obviously this is the forward reaction. This is the forward reaction. And the blue is obviously the reverse. What I'm saying is that with a temperature increase, all right, or even if you increase the pressure, whichever one, temperature increase or increase in pressure or temperature, the rate of equilibrium reaction immediately increases. Okay. So even if you, so you can see here, T1, all right, the rate of the reaction increased. Okay, here's T1. I'm going to use a, okay, here we go. This is T1. And over here you got T2. And over here, at this point here where they meet, that'll be T3. So immediately there are increases to both the forward and reverse reaction when there is an increase in temperature, but we can obviously see which reaction is mostly favored, the reverse reaction, because it's favoring, it is favoring the reverse reaction, which would be endothermic. All right, it'll be endothermic, okay, because that's under the theory of Le Chatelier's principle, the attempt of the reaction to counteract the effect to the change in equilibrium. Okay, not just the change of the rates at which products are formed, but now we're trying to counteract equilibrium now. So if we can understand that factor, we won't get too confused with what's happening with why the reverse reaction would be favored if there's an increase in temperature. So if the increase in temperature favors the endothermic, which is the reverse reaction, a decrease in temperature will obviously favor the forward reaction, which is exothermic. And I'll give you a depiction of that, how that looks when I get more deeper into Le Chatelier's principle. Okay, this is just a little crash course quickly. And that's all we have time for, grade 12s. Thanks so much for joining me on that little practice test that we did with one of our students tonight, as well as a quick crash course into Le Chatelier's principle.